Okay. All right, so today we're going to talk about chapter 2, which is potentials and thermodynamics. So we will think about thermodynamics. Now, this is going to be a rather cursory overview of the topic, quite frankly. But again, you've got to have enough fundamentals in you that you can pull it out to talk fundamentally about a potential and how that depends on thermodynamics, because almost all of you will have a chemist on your orals committee. We have way too many of them around here. We don't have a lot of other people. You know, it just is what it is. Like, you're going to have somebody who knows this stuff, and so you have to be able to talk fundamentals of like thermodynamics. We'll do chapter 3 tomorrow. Again, cursory, but kinetics. We've got to be able to talk about. Okay, so let's get some basic definitions. So the first thing we need to know is what is reversibility. It turns out there are a lot of different definitions of this word. It's not an easy word to kind of define. And if we're talking about reversibility, we never talk about reversibility unless we're talking about processes that are at equilibrium. So again, not at equilibrium, it's not going to be reversible. We don't talk about it like that. All right, so let's talk first definition of reversibility. All right, so that definition is chemical reversibility. So let's say we have this reaction, this equation going on. And this is all taking place, this hydrogen is taking place in a platinum electrode. But that's not the equation. All right, so we're having hydrogen going to H plus, H is going to H plus 2Cl. Right, so that's the natural direction it would go, but if we added a battery, right, we could then drive it back the other way. And so we had started with these projects. We would go back and we would make those projects. So, it would go back the other way. So that's the definition of chemical reversibility. This is chemically reversible. And that if I were to switch the potential, then I get the same products out, basically, that I started with. So we can kind of go back and forth. All right. However, we might start with a reaction like this. Again, that's like chemical cell. Oops. So that would be the reaction we might like to go. But if we were to reverse the potential, now we're going to get different reactions. At the zinc electrode, it turns out we're going to get hydrogen peroxide. H plus reduction hydrogen. At the platinum electrode, we end up getting water. Oxidation. Well, let me get my notes down. Maybe I won't write this out. And I thought, oh no, I will. I just pulled from the textbook. I will, because it's the only time I'll write out for you water oxidation. So there's water oxidation. We talk about water oxidation all the time as if we all know what water oxidation is. That's the reaction of water oxidation. It's the only time I think it'll come up with this. So I just went ahead and write it down for you. Even though we can obviously see, right, that this reaction is chemically irreversible. Meaning if we go one way and then we apply it and we get different products going the other way. And that again, something may be inhibited by the kinetics of the electrode, like it might be reversible at one electrode, but not reversible at another electrode. Again, it's going to do the process that kind of has the best potential to kind of go there. And so we just learned about coupled chemical reactions. So if you produce a radical, it's almost always irreversible. And the reason is, right, because you do a chemical reaction almost always. Right, so radicals are really unstable. They usually undergo a chemical reaction. They may fall apart. They may react with each other. If you're doing any of that kind of stuff, those chemical reactions, you're not going to have a chemical reversible process because it's going to already gone on to something else by the time you decide to reverse it and go back. So again, that kind of links the couple chemical reactions. Okay, so that's for chemical reversibility. That's all well and good. There's another definition of reversibility. And this is the one that's a little hard to get your head around. But I'm sure we were all chemists, we were recent. So this is the thermodynamic definition of reversibility. And basically, if you have to be at equilibrium, this says if you have an infinitesimal reversal in your driving force, we'll talk about that in a moment, think delta G, then that will reverse the reaction. Again, I don't find that one to be very useful, like to think about very much. But basically, it says if you were driving at this speed, you started to try, reverse the driving force, it would go back the other way. What this means is to be thermodynamically reversible, you must be chemically reversible. But you can be chemically reversible and not be thermodynamically reversible. Meaning you're never going to satisfy this if you don't get the same products out. You can get the same products out, but have it be slow, have it be not, fully reactive or something like that. And so it's not officially dynamically reversible. Luckily, the definitions don't stop there. Because the last definition is practical reversibility. So as you can imagine, it's the practical definition. That's the one everybody uses to actually tell you whether or not it's reversible. And the practical definition of reversibility is does it follow the Nernst equation. So let's look at the Nernst equation. We're going to derive it. Of it. Right, this is always our definition. Oh, that's O and that's R, right, from the reaction. All right, so that the E that you get out should be, we'll talk about this in a minute, heroic concentrations. This is called the formal potential. Plus RT over NF times the concentration of O divided by the concentration of R. So does it follow that? If it follows that, and again, you'll see and read, if you read through electrochemistry papers, you'll often see I had Nernstian behavior or whatever. Like that's what they're saying. It was reversible. It followed the Nernst equation, and that's like the highest praise, right, for an electrochemistry reaction. It was Nernstian. It followed the Nernst equation. That's the kind of like skill of improvement. My electrode was Nernstian for this reaction. You know, it did what it was supposed to do. That's what they basically say. Just not the practical definition. Okay, so let's talk thermodynamics for a minute. When you took P-Chem, maybe not everybody's taking P-Chem. Mild and possibly not have. You learned this definition. Or delta G, right? So that should look really familiar, hopefully. This is delta G. So what's delta G, right? That's Gibbs free energy. It's maximum work obtainable, which is other than PV work. PV is pressure line. So that's the maximum work attainable from the system. And that's the definition you learned. And it turns out that in electrochemistry, this is a very practical definition. But I mean, people do like use calorimeters and stuff. I've done this in the P-Chem lab, which you can measure delta H, T delta S. Right, this is the entropy term, that's the heater, and the information term. So those are all well and good. But it turns out that the more practical definition for electrochemistry ends up being this. A delta G is equal to NFE. For right now, I'm going to have some frames in this. So we don't think about it. We're not going to think about springs. Sorry, wow. So delta G, so NF, right, is just charge. Passed, and then this E, right, is the potential. So the amount of work you do depends on how much charge you have to move and how much potential you apply. And if you know this equation, because of sign conventions, we're going to go with the minus sign there. On there. Okay, so if everything was at unit activity, meaning all the activity coefficients were 1, right? We would get a standard state delta G, right? So if this delta G0, like everything else is just kind of the standard state delta G. And so, right, we can write that would be equal to minus NF E0. And so, again, this E0 then is the standard electrode potential. And again, this is all assuming activity coefficients are all equal. Okay, so then another definition of delta G. This one I think might have seen, but it's probably not the first one your P-Chem professor wrote on the board. So hopefully that one looks pretty familiar too. So delta G is equal to delta G0, right? The standard thing plus RT times ln of K. So this is our equilibrium. So now, right, in the equilibrium coefficient, which we sort of did over here, we did in concentration, something like that, allows us to, change around the concentrations, not all have all of them be a unit activity that tells us how much it's going to, delta G is going to, vary from the standards. Okay, so we have two definitions for delta G. Yes, two definitions for delta G. And we can make them basically be equal to each other. And if we were going to do that, we would end up with this. So this would be here. That actually ends up getting you reaction. So we kind of go from there. Sometimes people write it as K, some people write it as Q if it's not at equilibrium. It won't matter today. But we can kind of make them equal to each other. And then if they're not at equilibrium, we use this equation. And you end up with kind of solving that. So again, that gets us back to that. Excuse me. Gets us back to the Nernst equation. And so, again, it's kind of weird because we're electrochemists. I don't know if anyone is with Nernst equation. But it's like you can't not know it. And you can't not have some idea that's based on delta G. And that there's some standard definitions of delta G. Basically, you put two of them equal to each other, and that pops the Nernst equation. As far as that goes, we don't solve it all though in this app. Okay, so it turns out right that people really hate activity coefficients. So like you and I mean, if you have like this reaction. You would have some sort of coefficient right in front of all of those, and you would write out, okay, delta G is equal to delta G0 plus RT plus natural log the activity of R times the activity of H plus H power plus activity of O to its power times the activity of H2 to its power. Now, why did I put in the hydrogen here? Right, remember what I said yesterday? That, right, is our standard hydrogen electrode. So this is standard hydrogen electrode by definition. Those activities are going to be equal to 1, right? So that would cancel. But nobody likes to work with an activity coefficient. And so, so instead, they've come up with a concept of formal potential. So formal potential has that little slash. So you see E0 with like a little, I don't know, apostrophe slash after it. That's not the standard potential. That's the formal potential. And so, so here, basically are going to define not the activity coefficient 1. We're going to define kind of that 2. And then we have to define the concentration of everything else. Meaning you have to define the concentration of the electron. And that's important because the electrolyte changes the activity coefficient. So, again, it's one of these things, whenever you teach this, you always teach people about like activity coefficient and then nobody uses them. Almost nobody uses them if they don't have to. But, all standard definitions are of activity coefficient, and then when they move on. But a lot of times when people don't really, they're like, I don't know, I see E0, I see that I really have no idea what the difference is. Usually, formal potential is usually approximately equal to that standard potential. So they're usually not very different. But, of the absolute correctness of it, the standard potential is the one that you can define absolutely correctly. The formal potential is a little more difficult because of the activity coefficients. Yeah. So I said this, I want to raise it again, that the electrolyte matters easier to find, again, can be different in different media. Every once in a while, you'll look up, if you should get out a book and just look at the standard electrode potential table. I know it's kind of boring at the end. It's in like every analytical textbook. If you look at it, a lot of times what it'll do is sometimes it'll tell you like something in the like 1 mole rates. Or this or that, it's trying to give you like easier to find that as far as that goes. Okay, so that's delta G. Moving on from delta G. Next stop is chemical potential. Anybody remember chemical potential after explorations? Do you not bang chemical potential into your head? Anyone know the definition of chemical potential? It has to do with delta G. I'll give you that much of a hint. Seriously, did you talk about it in separations?
A little bit, vaguely, try to recall.
All right, so the definition of chemical potential, which I highly recommend that you know, because it's not hard, is this. Is the change in delta G or change in number of moles is the number of moles of analyte, and so in this case I is. And so we give chemical potential the symbol of mu and alpha here talks about phase. So chemical potential is going to be different in different phases. So if you're in water, it'd be one thing. If you're in methanol, it'd be something different.